So this is the PDE course. So please stop me when there is something that you don't understand. Anything that each time you don't understand something that I say or I write, please stop me. Okay? Partial differential equations. Let me give you some reference. References on this. Maybe we can start from. I will not follow a specific book actually. So, but one book which is usually we should take into account is the book of Evans. And the title, I think, is Partial Differential Equations. Or there are other books. And many others. But I am not following any specific book. In any case, these are suggested if you want, if you are interested. So partial differential equations is a field which is sort of so big that it's even difficult to say something general. There are the motivations for studying PDEs can come essentially maybe from applications initially. Mathematical physics is based on the study of partial differential equations. Problems in electromagnetism are usually based on the study of elliptic partial differential equations. Heat conduction is associated with parabolic partial differential equations. Wave evolutions are associated with hyperbolic partial differential equations. And then there are many, so usually people divide roughly these are not the only possibilities. There are intermediate equations or equations with change type. In some regions are hyperbolic, in other regions are elliptic. So there are a lot of different type of PDEs, and each type maybe requires a particular special theory. So, but still they are related to each other. This you see this in the potential, etc. This is heat conduction. This model waves. Just to say something, then there are systems of PDEs. So the story. So one has to find an origin, a place to start with. And I will start from one of the simplest case, still rather interesting in my opinion. So I want to start with, so these are all second order PDEs, wave equations. This is second order, usually second. But hyperbolic PDEs can be also first order. So I want to start from first order PDEs. First order is the simplest, maybe the simplest case. So first order PDE. So then we will come to second order in the next lectures. But for a few lectures we will do first order PDEs. Okay. And then we start with the linear case. So linear first order, just one PDE, so scalar, linear PDE, and we start with the following problem. So given in hypersurface sigma, actually hyperplane in R1 plus n, given a vector field, constant vector field, given function u 0 from sigma into R, u0 of class C1, so these are the data of the problem are these three data. 1, an hyperplane. 2, a vector field. 3, an initial function, sufficiently smooth. Find solution, maybe one solution only. 2,
this part is not appearing in the video.
Ah, this part?
So, yeah.
Sorry. So this doesn't, where?
Yeah, a little bit.
Like
Yeah,
here?
more. Yeah, you can see.
So, thanks, because I didn't know this. So I have to avoid, so I rewrite here. So these are the data of the problem, an hyperplane, a vector, and an initial function. The problem is to find. Now I will explain why this strange 1 plus n, and I will explain everything, okay? So find u, a solution, maybe unique, in this case, to the following problem. U C1 1 plus n, ut plus a dot grad u equals 0 in 1 plus n, u 0 z Okay, let me explain you. So we are sitting in R, say, think for simplicity n equal 1. So we are sitting in R2. We split R2 as follows. So we write R2 as 1 plus 1 when n is equal to 1, just the simplest case. The first component is time, so this is R1 plus n. First component is what I call t, let me call it time. Second component is the vector x. Okay, so x is x1, xn. In this simplest case, we just have n equal 1, and I call x1 equal x. Okay? Sigma is assign this surface, this line. So it's curious. T is the first component, but I draw it vertically. Okay, so we take this convention. Even if T is my first component, I like to draw it vertically. Okay, just a matter of deciding just convention. Okay. Then I give you a vector. This is in Rn. I give you a vector in Rn, call it A, non-zero, just for otherwise. And then I give you a function u0, which is defined only on this violet line, and it is given. The only requirement for me is that this u0 is sufficiently smooth. Okay? C1, say, for the moment. Given these three objects, I ask whether or not we can find a solution with the following properties. C1 in time space, so this is time space. Solution of these linear partial differential equations. What does it mean, ut? Ut means du over the first variable. Grad u is, by definition, the vector, the gradient, du over dx1, du over dxn. And this is the standard canonical Euclidean scalar product. Okay, so the PDE actually is ut plus sum 1 to n, so u over dt, if you like, u over dx. This is more explicitly how the PDE can be written. So I have a PDE, I ask for a PDE valid in the whole time space. I ask that u is smooth enough, because otherwise it's difficult to give a meaning to these partial derivatives. And then I ask that on this initial sigma, u is assigned, is given, must be given equal to this. Okay? This is called the linear transport equation. And we will see why it is called linear. Linear because it is linear. It is linear in u, t. So u, the derivatives of u appear linearly. It's not like, I don't know, u x squared. It's linear. ut appears linearly. The gradient is just appears linearly here. There is no nonlinearity. Okay. Linear transport equation. Actually, this is homogeneous because the right hand side is 0. So linear homogeneous transport equation. Homogeneous. With constant coefficients, because this, we can imagine that this, we can imagine to have 1 here in front. So the coefficients are 1a, if you want, in R1 plus n, constant, with constant coefficients. Is this clear? The problem? How can we rewrite this PDE? So this is our problem. let me do some remarks. Let me tell you something. Okay, problem given, etc., etc. So I can draw the vector. So let me give a name to this vector, capital A. Okay. So capital A is a vector in Rn plus 1. We can imagine actually that at each point we have this vector. So say, for instance, at any point, this is a constant vector. This is A, this is 1. So this is vector capital A. We can rewrite this in various ways. So first remark, this equation here can be rewritten, for instance, as follows. The scalar product between A and the time-space gradient of U equals 0. This is one way. This is the time-space gradient. Okay, so it is an 1 plus n vector. This is one way. Another way in which we can write this is ut plus divergence of UA, divergence in space equals 0. No? Because the divergence of this is a scalar function, this is a vector. Remember that if I have a scalar function f and the vector field, everything is smooth enough, then I can expand the divergence as follows: grad f dot v divergence of Well, we recall, if you don't remember, the divergence of a vector field is some dr. By definition. So this is another way to write the PDE. This is interesting because it has a geometric meaning. Because it says that the time-space gradient of U must be at any point orthogonal to this vector field. It is written here. We will come back to this in a moment. Divergence in space, say well. I can also write this as the divergence in time space of U A. Divergence in time space, let me check. The gradient in time space, yes. Okay. Do you agree with this? This is divergence in time space. So we can write, of course, everything works here because, so this is called, say, maybe continuity equation. It is in divergence form, and this trick can be done simply because A is constant. It is clear that if A is a vector field which is not constant anymore, so if A depends, say, on t or on x, then this is cannot be written so simply, clearly. But as soon as A is constant, when I differentiate it, the differential is always 0, I can do this very easily. Okay? Nice. Now let me come back. So let me come back to this maybe. formulation. This formulation. Maybe some notation. I will write U0, usually I will write U0 of Z instead that U0 of 0Z. For simplicity. Okay? Okay? Because sigma would be a 0, comma Z. We are here on sigma. So let me write simply U0 of Z. Okay? In place. So that I can write this as now. Let me come back to this formulation. So now we have our time space. There is a vector field which is constant, fortunately in this case, over this vector space. And there is also one comment which is important here, is that A is not tangent to sigma, clearly. Why A is not tangent to sigma? Because capital A has first component, which is 1. As soon as you have a vector with first component, whatever A is, small a is, if here is 1, this vector has some vertical component and therefore is not tangent. Okay? So we say, in other words, that capital A is transverse to sigma. This is fundamental in the theory, crucial assumption. This is a crucial fact, and this crucial fact gives you a sort of interaction between this, because the problem is I give you a vector field, I give you sigma, I give you U0. But sigma and the vector field must be transverse each other in order to do this theory. Like in this case. Clearly in this case, sigma is very simple, it's a special hypersurface, it's just flat. Capital A is very simple because it is constant, and it is never tangent. Okay? But if you would like to do a generalization of this, which means take any hypersurface sigma, take a general vector field, then you have to suppose that usually that the vector field must be transverse to the point of sigma. So, namely, if your sigma would be, say, this one, this is new sigma, then you have a given vector field, okay, this given vector field maybe changes somewhere, I don't know, but never tangent to sigma, okay, this no, this is a problem. Okay, so we can assign some smooth vector fields. We are sitting in the simplest case. Sigma is flat, vector field is constant. Okay, to start with. In general, if you look in the books, on first order partial differential equations, characteristic method, etc., you find much more general cases. But for just to begin to understand, in my opinion, it's better to start from here. Are there questions, comments? Everything is clear? Completely clear? So, now, let me go back. So there are various ways to see this PDE, 1, 2, 3, etc., 4. But let's look at this now. We can recognize something here, because this says that the directional derivative of u in the direction capital A says directional derivative of u in the direction given by capital A, so if you want in A divided by its norm, because you know, no? I mean, you have a representation of the directional derivative. The directional derivative of a function, the derivative of a function along a direction is the scalar product between the direction and the gradient. Okay? So I have a scalar product between the gradient, and if I want a direction, it's sufficient to normalize to divide it by the norm of A, which is not zero. I can always do this. So it must be zero. So what does it mean that I have a function defined in time space? I have a vector field on the time space, and I know that the directional derivative of the function must be zero everywhere. What does it mean?
It means that it should be constant
along the lines. So we expect, if a solution exists, if a solution to this problem, the most relevant, maybe, the first condition is very relevant actually. Don't forget the first condition. If we expect a solution, if it exists, to be constant on all lines parallel to A, right? So in our picture, fortunately capital A is constant, so the curves that have capital A as a tangent are just lines parallel to capital A. So capital A is, say, this point here, A1. So I take all these lines, and U must be constant here, right? This is sigma, capital A in R3, that is in R2, this is in R3, etc. This is time. So in 2 dimensions, in n equal 1, these are lines where u must be constant. So the value of u here must be equal to the value of along all these lines here. In particular, the value of u here must be equal to the value of u here. Right? The value of u at tx here must be equal to the value of u along this line. The value of u here must be equal to the value of u in particular at time 0. Okay? This is what the equation is saying, provided u is C1. Is this clear? Of course, if you are in 3 dimensions, sigma is a plane now. No? And the lines are still lines, and u must be constant on each of these lines. These lines now have codimension 2 in R3, this line has codimension 1 in R3. There is a difference. Remark. All this line, trivial remark, sorry, because we are in a trivial situation, but still, why not? All these lines are disjoints. On each other, they are parallel, and they fill you take all the lines, you fill all the space. Okay. Okay. Now, I have to say things in a certain order. So now, can I erase everything? No? If everything is clear, we can go on. So A dot, this is the PDE, equals 0. Okay. Okay, I could, if I want, well, no. Let's state the following theorem. Theorem 1. The problem has a unique solution, which unfortunately I just erased, has a unique solution given by u of tx equal u0 ta for any tx in 1 plus n. So this is a theorem which says everything, because not only the theorem says existence of a solution, uniqueness, and representation. So it says everything. It represents the solution in terms of the initial condition that has been given from outside, has been given from the beginning. Okay? So this is existence, uniqueness, and representation. Regularity. Regularity means in which class existence, uniqueness, and representation. So we have an explicit solution. Say, let's see why. Okay. Let us first check that this is a solution of our PDE. One solves our problem. Why? Well, U0 goes C1 by assumption. This is a linear. Composition remains C1. This is clear. What happens at time 0? When I put t equals 0 here, I get u0 of x. And so also the initial condition is attained. This is okay, nice. So we have, it remains to show that this u solves the PDE. Okay, so let us compute the partial derivatives. du over dt. If I do the partial derivative of u with respect to t, I have to use the chain rule. So this is the gradient of u naught and then I have to multiply by the derivative with respect to t. So it is minus dot t. Okay. Moreover, so this is the u, then I compute the partial derivative with respect to xi. So what do I get? I get simply the partial derivative. So this means that grad u dx is equal to Now, the PDE was the following: ut plus a dot grad u equals 0. And now I immediately check that ut is this minus. And if I compute now the scalar product, so if I compute this right and this term here, then this is equal clearly to grad u0 times a. Of course. Therefore, this is equal to minus, from this equality, this is equal to minus. Okay? And therefore the PDE is satisfied. Okay? Now, in the order that I want to say things, I will tell you these things later. So, this shows that this is a solution. Now, let us show that all solutions must be of this form. Okay? This was trivial. What it is interesting is the second part. So, can I go on? Is this clear? Okay. So this is a solution. Now, suppose that you have one solution of our problem. We want to show that this solution must be equal to this. So let me call u. So now let u be a solution. And now the idea is to restrict u along these lines. No? So fix a point tx somewhere. So I fix a point and now I move along the line parallel to capital A, passing through this point. So I can parameterize this line. This line I can parameterize with a parameter, say, which I cannot call t because t has been fixed before. So let me use another symbol. So tau in R, I parameterize it, that goes into tx plus tau a. Okay? When tau, if this is a, when tau is equal to 0, I am at tx. When tau is larger than 0, I am here. When tau is less than 0, I am here. Okay? So, or in other words, this is also equal to t plus tau, remembering that capital A was defined to be 1 small a. Okay, this was the definition. So this is t plus tau, x plus t a. Okay?
Tau
Ah, yes, thanks. X plus tau a. Thank you. So what does it mean now taking the restriction of this phantomatic solution u that I want to show to be equal to this? Restriction to the line means that I have just function, so let me call it f, which is the restriction of this hypothetical solution to my line, okay, passing through tx. X plus tau. So let me consider, so U is C1, let me consider this, and clearly also F is C1. Hmm? F is C1.
Is it constant?
Hmm?
Is it constant?
Pardon?
Is it constant?
F, yes, clearly. Now, of course, you have understood because this is a simple case, but let me prove it is constant. Correct remark. F prime of tau, as it is expected, must be constant because it's U along this line, and we already have understood that along the lines U, any U must be constant because it is written by, it is something that your PD is saying. Okay, let me compute it. So ut t plus tau x plus tau a plus, now I have to differentiate this, and you get u t plus tau comma x plus tau a, and this must be 0. Is 0 because ut plus a dot grad u is 0 at any point, in particular at this point. Okay? So this is 0, so this means that f is constant. Okay? What does it mean that f is constant? Well, this means that f of tau, for any tau, is equal to, say, f of 0, for instance. Okay? So f of tau, here, here at some tau, so here, I am here at time 0, right? At tau 0, at tau 0, I am here. So this must be u of tx. Trivial, because if you put 0 here, you get u of tx. So this is equal to u of tx. Fine. And I know that u is constant at this parameter tau must be equal to this. But I have now to use that my initial condition. So it's enough that to say that the value of u here is constant, in particular must be the value of u here. No? And the value of u here, how do I get this? Well, in this picture, I get it evaluating this at minus t. No? So this must be equal, since it is constant, I imagine to travel backward along my parameterization of the line, to travel backward of a quantity which is minus t. So what happens when I take, so u of tx must be also equal to f at minus t. So I put minus t here, and I get 0, comma, x minus ta. Which, however, we remember that on sigma, u must be equal to u0, because u is a solution. U is a solution. So, u is a solution. So this must be equal to u0. And now you forget everything, but recall instead this. And you end up with the proof of the theorem. Okay? Remarks. Now there is a long list of remarks. If this is clear, so this concludes the proof, and quite easy. but let me do some remarks, okay? Okay, remarks that apparently are not useful, but maybe for the sequel they sooner or later will become useful. So, remark. Let me introduce another vector. Consider the vector A0, capital A0, which is now sitting in R1 plus n plus 1. Okay. R plus n plus 1. Our PDE is saying was A dot ut where u equals 0. Okay, well, it can be also written clearly as the following in this form here, in R1 plus n plus 1. This is the space of graphs. What does it mean, graphs? What does it mean? It means that the graph U is by definition Tx U of Tx such that Tx is in n1 plus n. So this is the graph of U, by definition. So, and this sitting, since this is in n1 plus n, 1 plus n plus 1. Okay. I want to look at the graph of the solution. So now I invent another vector field. This vector field was in n plus 1, 1 plus n. I add a component, 0. Ut, grad u, say minus 1, divided so we can write in another form, fifth form, the same PDE in a more geometric way. Why? We agree that this scalar product is equivalent to this? Well, simply because 0 kills this last component, and so it's clear that nothing changes. This is clear, no? But why I am introducing this strange object? Do you recognize what it is, this strange object?
The norm of the...
This is the unit normal to the graph of U with negative last component. No? So if I have the graph now, it's not so easy to let me try. Now that I am in the space of graphs, I change the way of drawing. Remember, before t was here and x was here. Now I have also t, x, another coordinate, u of tx. So now tx becomes, so this plane here, now let me put it horizontally there, so that u of tx is the vector, as usual when we draw graphs. So this is u, if you want, t and x. Okay. So now I have some u0 here, no, u0. Then I have my vector field, it was A, capital A was vector field constant here. And now I don't know if I'm really able to write down sort of u of tx. So so let me tell you that this, say, is the graph of u of tx. So tx to variables, the graph is a surface. So this surface here is the graph of u. This initial object, this was sigma. And U0, the graph of U0 is this. U0 takes sigma into R. Okay. So and then, okay, one should continue behind. The time is positive and negative, so okay, there is something. Okay. This is sort of picture I can do. Is it clear? Oh, now, so this U0 is given, sigma is given. My PD is this now, is equivalent to that. And why I write this? Because this has a geometric interpretation. It means this is actually now I take the normal. This is what is this object here, as he said, is the normal to the graph of u at the point tx u of tx, unit normal. Of course, if you have a surface, there are two units normal, one and the opposite. No, I'm taking the one with the negative last component. Yes. So I have so here, for instance, this is new, and here maybe new. No, this is maybe here new. Huh? With negative last component. So this tells me that if I look at the graph of my solution, the graph must have the normal orthogonal to this. Or equivalently, this must be in the tangent space to the graph. At any point. So, this is interesting because you see, what are we looking for, geometrically speaking only, is the following. We have given this curve here, which is the graph of U0. Over sigma. So we have given this curve, which is graph over sigma. This is a curve which in R3 has codimension 2. 2 codimensional. Have given this, have given this vector field, given constant for the moment. Actually, when I write this, I am identifying this with its tangent space. It doesn't matter if you don't. Given this, I'm looking for a hypersurface. So geometrically speaking, our PDE expresses the problem in geometry, looking for a hypersurface of graph type, not any hypersurface, but of graph type, meaning graph of something, and this something must be C1. So let me call graph type C1 with the following properties. It must contain this is codimension 1. Hyper means codimension 1. This has codimension 2. This has codimension 1. Like in this picture, I have given a curve which has dimension 1 and therefore codimension 2. Look for a surface which has dimension 2 and therefore codimension 1, which contains this, that graph, containing graph of a knot, and having in each tangent space this vector field. In each of its tangent spaces, the vector is here. This is a problem. Geometry of surfaces or hypersurfaces is equivalent as soon as everything is smooth to what our PD is saying. So you have here, now you see, our vector field given has 0 vertical component. So our capital A is always, there is no vertical component, no? So, at the end, how this surface can be constructed? Well, simply you have your initial condition, your lines, and you rigidly translate your initial condition producing a surface in the direction of the lines, backward and forward. You transport your initial condition along the lines. This is called, why it's called transport equation. This is just geometrical picture. Yes?
Do the name transport equation come after the solution of the PDs or just from the geometric interpretation of the...
I imagine after the solution of the PDE. I imagine. I insist on this geometric interpretation because for me, as soon as there is the geometric interpretation, it becomes easier. But I think that there are several other reasons for which this is called linear transport equation, and I think that this reason comes from directly looking at the PD. Okay? Is this clear? Now, these lines, I have to say, have a name, are called maybe projected characteristics, the lines that live in the horizontal space here. This parallel to capital A. They are called projected characteristics, but this we will see later. Okay, so this is a first remark on interpretation of the PD. Next. There is another remark. This PDE, this is a remark that is interesting because it's related to regularity, remark. This PDE has no regularizing effect. What does it mean? Which means that if I start with an initial condition with a certain regularity, U0 was C1, sigma. The solution does not improve the regularity. Is at most regular, at most as it was. Cannot be more regular than U0 itself. And not more. Well, why? Simply because the solution is U0 at x minus t. So if U0 is C1, U is C1, but not surely not C2. No? Simply by the representation. Because this is trivial. If U0 is C1 but not C2, this cannot be C2. It remains as regular as it was. It could, in this case, it remains as regular as U0 is, essentially. Another remark, if U0 is less than 0 on sigma, then U. Okay. This is another remark. Okay, now coming to something maybe more interesting than this, we can introduce the following system. The system of characteristics. So because now, of course, we started from a very simple situation, we want to understand everything in this linear, constant coefficient situation. Once we have understood this, we can go on. So it's better to write everything in this initial case. So let me consider the following. So let, say, Z in Rn be given. And consider the following, system. X dot, dot means d over dt. Okay. So x dot of 0 equal A, x of 0 equal Z. Okay. These are n ordinary differential equations. No? Consider the solution x from R into n, Rn, yes. X dot of 0 equal A, x of 0 equals Z. This is a very easy system of n differential equations decoupled. This is a vector in Rn, this is also a vector in Rn. The solution is trivial, no? X of t is given by what?
Is it x dot of t?
X dot of t. So, x dot of t. Solution is what? Z plus TA. No? So, this is called, maybe in this case, what is this? Well, these are the flow lines of the vector field small a. So we look at those curves having small a tangent to small a. This is a system of ODEs. We have curves now. And these curves have all, of course, the usual lines. These are the famous lines that we have studied before. Let me denote it by, but I have a parameter. So this has a parameter. So let me denote it, actually two parameters, 0 and Z. So let, if you want, better than this, let 0Z be given in sigma, okay? Instead, maybe slightly better. So 0 and z are given. I have two parameters, 0 and z. I could denote this solution as x of t semicolon 0 z, because this is a parameter. Actually 0 here is not so important, so let me simply denote this, more simply, x of t semicolon z. So given z, a parameter in Rn, we can produce a unique solution of this form. Trivial in this case, do you agree? But this is, let me call this, these are called the, no, this is not called that because it is too small. Okay, let me add to this system another system, now scalar, y dot equals 0, y of 0 equal u0 of z. Of course, the solution is trivial in this case, because this must be constant, so y of t must be constant equal to z. Y of t must be equal to u0 of z, in this case, for any t, trivially. Let me denote this solution by y of t 0z, or more simply, y of t semicolon z. Okay, so now finally system 1 and 2 is called I don't know if it is characteristic or characteristic system. Okay. The system definition is called the system of characteristics. Starting from, well, this starts from z, and this starts from u0 of z. The map T into is called projected characteristic starting from Z. Instead, the complete system, the map T into R, comma T comma x of tz, and the map T going into T comma x of tz comma y of tz is called the characteristics. Is called the characteristic. Not projected is the this is projected because I forget about this last component. I just have T capital X here, just T capital X. But if I consider also the last component, which is in this case very trivial, is called characteristic. Characteristic starting from Z, U0 Z. Okay. So, starting from now, we have slightly changed the viewpoint. From instead of looking about a PDE, we are now looking at systems of ODEs. And we want to look at the relations between our initial PDE and this auxiliary system of ordinary differential equations. How many equations? These are n equations, and this is one equation. Just one equation. Okay? Okay, now, before going on, let me introduce another object which at the end is one of the most important objects. So I have defined the projected characteristic, which is this map. So in this specific case, this map is simply T that goes into Z plus TA. In this specific case. Instead, the system of characteristics in this case is T, Z plus TA, comma U0 of Z. Okay? This is how the solutions of these systems of ODEs with the parameter Z are. Everything is explicit here. Okay, now let me introduce, once we have spoken about this, I can finally introduce a map, diffeomorphism. Other comments or questions, something which is not clear? Everything is clear? So that you can go home without doubts. Everything is clear? Now you will see why. What it is not clear maybe is why I am doing this capital X and Y. I have introduced the system. You will see in a moment.
I think it is a specific case of method of characteristics.
Pardon? This is a very special case of the general method of characteristics. Yes.
For force order.
Yes, exactly. I want to illustrate in this linear case because everything is explicit, everything is linear, so computations can be done. Once we have understood here, we can go on to more nonlinear cases in which the system is much more complicated. Okay, but this is exactly what you said. Exactly. Okay. So definition. So let me denote by phi, capital Phi, from the following map. In this very specific case, this is simply T Z plus T. In this case, okay. Now phi is a diffeomorphism, linear diffeomorphism in general, so is invertible, globally invertible. So, and phi minus 1, it can be easily checked. So, let me call this so phi minus 1 goes from here to here. Has the following structure. So I think I call this maybe Z. Okay, yes. Let me check if my notation is yes. Capital Z. where capital Z of Px is the inverse, where Z fixing T, this is the inverse What I want to say is the following. This is the solution of the projected characteristic, right? This is the projected characteristic. Remember, if you look at your notes, you find it is a projected characteristic. So, in particular, in this specific case, it is this, because we know the solution, the projected characteristic is this. Okay? Fine. Now you see, I'm sending Tz into Tx, and X has this expression. It is clearly a diffeomorphism. And it is globally invertible, right? So I can consider the inverse. It is the identity in the first component, this diffeomorphism. It's a very special diffeomorphism because it is level preserving. It preserves T, goes into T. So it's not any diffeomorphism. It's very specific because it is the identity in the first component. But still, also the inverse, what I'm saying is also the inverse has this property. It is still the identity in the first component. And the last component is just the inverse of this. In this case, it is immediate to check that the inverse of Z plus TA is this. No, this is trivial. You add and subtract TA and then you come back to where you start from. Okay, I don't give a name to this. Okay. Nice. Now, this is, this will be much more general than this in the linear case, but for the moment we keep this trivial expression and this also the inverse is explicit in this case. But the remark, maybe the remark which makes this rather interesting is the following, is that the solution U of theorem 1, I think it was called, the theorem that we made, existence, uniqueness, and representation. Theorem 1 can also be written equivalently, be written as U of Tx equal Y of T Z of Tx. This is something that you have somehow to. Now let us check that this is true in this case, which is actually very trivial. Why it is so? Let us compute Y of T, Z of Tx. Remember that Y was constant. Y was U0 of Z, right? Starting. So this is U0 of capital Z of Tx. But capital Z of Tx is the inverse. So this is equal to this, right? It is written here. And this is the content of theorem 1. What is the moral of the story? This is trivial in this case, but the moral is deep. Let me try to tell you the moral of the story, if I am able to do. Do you accept this? Now this is a little bit more involved because we are looking at solution of system of these, even if they are trivial, system of these with parameters, the inverse, it's a little bit more involved. Still, your moral. Moral. Model. So I have my vector field, I have sigma, I have my vector field, and I have U0. These are the data of the problem. Sigma must be transverse to A. Because if it is tangent, it is clear that the method breaks down immediately. Okay. So we have sigma, we have our capital A, transverse. Once we have capital A, we can solve a system of ODEs which has the following form. It is the flow line of this vector field. What does it mean? I find all curves having this vector field as a tangent. This is x dot the analog of x dot equal A. The trajectories of this system of these before were lines are nothing but those curves having A as a tangent vector. No? This is system of these geometric interpretation. So we find these lines, these curves in general, in this case lines. Now we have produced a foliation of in this case we have foliated the whole space R1 plus n. In general, maybe this can be done only locally, but in this case globally. Now these foliations gives us a diffeomorphism, capital phi, Tz into this. This diffeomorphism can be inverted, producing this, and my solution at this point will be the value of U0 going along the inverse, capital Z, and computing U0 at this point. This is the model. In this case, everything is explicit. I am foliating the whole space. These flow lines of the system of these are rectilinear. Everything is very easy and explicit. Okay? This is another very useful interpretation of our initial PDE. Okay? So now an interesting, see?
So this means that in the case where the vector field and the original hyperplane are not tangent,
Transverse.
Transverse.
Are not transverse.
Are not transverse.
I don't know the answer. If they are not transverse, you fail to have a diffeomorphism.
No, I mean if they are transverse,
yes.
If they are transverse, then the solution is always doesn't have the regularity.
More than
Never,
because you transport your initial condition with that regularity along these curves. And that's it. Regularity remains the same in this case. But it can also become worse than that. In this case, it cannot. But assume that you are so unlucky that you have a PDE for which these flow lines instead of being parallel, they are transverse, but at some moment they intersect. You can imagine, I mean, not this case, other PDEs, you cannot exclude that your vector field A maybe depends on t and x, so the slope of the curve changes. And you can imagine that maybe here you have a slope, here you have another slope, here another slope, and at some moment, now the situation is much more serious. Here you start maybe with a very smooth initial condition, but if you have this situation, who knows? What about the regularity of the solution? Things can go worse in that case. Not in this linear constant coefficient case, however. Okay? I insist because very interesting problems arise when characteristics intersect and cross each other. These are very interesting points. Because you don't know, I mean, when you are here, you cannot use anymore the idea of going back. Because you don't know if you have to go back here or here. Where do you go? No? So what is the definition of solution? You here, you know. We don't know. So this method fails. But not in this linear case for the moment. Okay, now last comment of today. Remember, the data of the problem were sigma, capital A, and U0. And now this problem is very simple. We have to generalize it. One possibility could be generalize sigma and the vector field. So instead of having an equal, you could imagine an embedded manifold. And A transverse may be changing point to point. This could be one generalization. Another is try to suppose that U0 is less regular than C1. Okay, so if U0, say, is less regular than C1, say for instance, U0 of Z, say, is U minus and U plus, I don't know, U minus and U plus, or maybe U minus could be larger than U plus, it doesn't matter here, but just two values. U0 now is clearly discontinuous. So what, if U0 is just very easy and important initial condition, taking two values only. These initial conditions are very important. Initial conditions taking only a finite number of values are discontinuous, but in general very important. What can we say about ut plus I of u equals 0, u of 0z, 0z, and then u in which class? And what does it mean being a solution of this? Because can we look for discontinuous solutions? Well, if we look for discontinuous solution, we cannot write the PDE in this form. Because we don't have pointwise derivatives for this simple reason. So if I give you a discontinuous initial condition, u plus and u minus here, graph over defined almost everywhere at all points except to this origin, say, existing. Or for simplicity, let me put u minus u plus here. Okay. I give you the usual vector field. What should I imagine? What happens to the solution? what is the solution? Is there a unique solution? Can we use the previous representation formula? If we use the previous representation formula, suppose that I pretend the solution to be as before. So, right? So u0 of x minus ta, as before. Well, u0 jumps. So this is discontinuous in time space. Right? So I don't know how to draw it, but it is something like, so here we go. There is a jump. There is a sort of I don't know, you have this object which travels and produces sort of surface with the vertical part flat, vertical, flat, in the direction of the characteristic lines. This is discontinuous, clearly, right? Well, if it is discontinuous, it could be a solution, but in which sense? We don't have these derivatives now. So what do we do? This will be the argument of the lecture of tomorrow. Okay, so it is interesting in general to start with initial conditions as general as possible. It's not just for fun, there are reasons for enlarging the class of initial conditions, U0. Okay.